So we are now going to discuss the real vectors of the whole heart. Okay, so we were discussing a part of the myocardium, how if the electrical activity is happening into that specific part, what will be, and it is connected with a galvanometer, so what will be the changes. Now we are thinking about the vectors of the whole heart. Okay, and what will be our learning objective. First we want to know what are the electrical events in the at the level of the heart. What are the electrical events that is happening in the heart in a one cardiac cycle, and how this electrical event we can translate it to the cardiac vectors, because galvanometer will identify the cardiac vectors. Okay, and how that specific vectors will be recognized, and what pattern of ECG will be ECG curve will be produced. So what are the clinical what are the electrical activity, how this electrical activity can be converted or translated into a cardiac vectors, and how these vectors are recognized by the ECG and a specific ECG pattern is developed. These three are our point of interest now. So first we want to know what are the electrical events that is happening in the heart, that we already know. So what are the electrical events that is happening in the heart? So the electrical event number one, it is we all know, it is the atrial depolarization. So as we all know that suppose this is my heart and this is my atrium, this is ventricle, and okay, and the electrical signal that is first generated, it is at the level of SA node, then it will go to the electrical window that is at the AV node, and followed by there will be stimulation of bundle of His and the Purkinje fiber. So in this way we can say that our first electrical event that is happening in the heart is our atrial depolarization. Atrial depolarization will be followed by what? The second event, that is my stimulation of AV node. Of AV node. Now after stimulation of AV node, what will be the next event? That is your ventricular depolarization. There will be depolarization of the ventricle. So the third event is ventricular depolarization. So when the whole ventricle is depolarized, the fourth event will be what? That is your ventricular repolarization. So these are the electrical events. First is atrial depolarization, second is the stimulation of AV node, followed by the ventricular depolarization and the ventricular repolarization. So these are the electrical events. Now we want to know how we can convert or translate this electrical activity into cardiac vector, electrical vector. And as I told you earlier, vector should have a value, specific value that indicates the force, electromotive force. It should have a direction, and you should say whether it is a fast vector or a slow vector. So these 3 points should qualify a vector. One is the force, how much strong is the vector. Second is what is the direction of the vector, and third point is how fast or slow is this vector. So first we will start with our atrial depolarization. So as we all know that, so again this is my heart and atrium, ventricle, and we all know that the electrical activity, it will start from SA node and then it will go to the AV node. So initially the cells nearby the SA node, they will be depolarized, followed by, so we know that SA node is situated at somewhat upward and to the right side of the heart. Okay, SA node is situated upward and to the right side of the heart. So when the electrical activity, it is gradually moving towards the AV node, we can say the direction of it is downward. It is downward and to the left. So many electrical activities, they will be added up, they will be summated, and ultimately we will get a single electrical vector whose direction is downward and to the left. And what about the force? So it is the length of the vector will indicate the force. This vector, as the atrial tissue is thinner tissue as compared to the ventricular tissue, so the vector length will be less. And what about the speed? As we know that these ventricles have some specialized conducting cells like Purkinje fiber, which has fastest conducting velocity, but no such cells are present in the atria, so their velocity will be slow. So how can we classify or qualify the atrial depolarization vector? Its direction is downward and to the left. It is small and of moderate velocity. Okay, so we can write it in this way. So the vector is directed downward and to the left. Secondly, it is small vector and the velocity is moderate velocity. Okay, now come to the point. So atrial depolarization is done, the electrical current has reached the AV node. So we know that AV node, what is the speciality of AV node? AV node, there will be AV nodal delay. Okay, so in the AV node is the only electrical window, because it is lying in between the fibrous annulus. This fibrous annulus is a bad conductor of electrical wave. So only and only through this AV nodal conduction tissue, the current from atrial depolarization will reach the ventricle. So AV node is the only electrical window. Okay, and the conduction velocity of AV node, it is slow. That's why there will be AV nodal delay. So we know that AV node, they will have a slow conduction velocity. So we will see that AV nodal conduction is a bit slow. So what are the reasons? Because AV nodal cells, they have less number of gap junctions, and if you look into the AV nodal cell in this way, suppose this is your AV node, the cells are like this, you will find out the current that is coming to the AV node, it is perpendicular. So when it is trying to depolarize the whole AV node, it has to face so many cell membranes. As it is not at the same parallel with the direction of the cells. It is coming in perpendicular to the direction of the cells. That's why it has to cross so many cell membrane, so many barriers of cell membrane. This also makes the electrical activity slow. Another point is that, so one is the direction of current is perpendicular to the direction of the cells and position of the cells. Third point is, we know that AV nodal is a pacemaker tissue. So AV nodal conduction, it is electrical activity, it is due to calcium entry, and calcium is the slow channels. That's why the action potential of the myocardial cell, it is known as fast action potential, and that of the pacemaker cell, it is known as the slow action potential. So that's why it is also slow. So these are the reasons why it is. And another important point, the resting membrane potential of these cells is minus 60 millivolt. Whereas if you see in case of ventricular cell or in the bundle of His, they have in the septum, the ventricular septum, if you look into them, so their cells, they are arranged in this way. So the first thing in the ventricular Purkinje cells, so when the current is coming, the direction of current is not at the perpendicular to the cell. So less number of cell membrane they are crossing. Second thing is that the generation of action potential in case of other types of myocardial cell, it is due to the entry of sodium. So sodium channels are the first one. In addition to that, all these cells, their resting membrane potential is minus 90 millivolt. So when the sodium is entering within a cell, if the cell interior is more negative, then the entry of sodium will be faster. Okay, whereas here the cell interior is minus 60, so positively charged ion, it will enter in a speed, but that speed will be higher if the cell interior is much more negative. So these are the reasons why AV nodal conduction, it is slow. So what will be the vector? Vector is a slow vector, and AV nodal tissue, AV nodal pacemaker cell is a very tiny piece of cell. That's why the vector is very small. And direction is obviously to the downward. Okay, so this is about the vector of this electrical activity, that is stimulation of AV node. Now come to the third electrical activity, that is ventricular depolarization. That is very important. So for it, we are drawing a ventricle here, a large ventricle like this. So here we have the AV node. AV node is connected to bundle of His, two bundle branches. One is the left bundle branch, another is the right bundle branch. Okay. So in case of ventricular depolarization, we have to divide it into three parts. Ventricular depolarization, we need to divide it into three parts. First is the septal depolarization, the depolarization of the septum. So first electrical activity is your septal depolarization. Followed by, there will be major ventricular depolarization. So when the septum is depolarized, the major ventricular part will undergo depolarization. So major ventricular depolarization. And the third one will be your depolarization. So when this whole portion is depolarized, the depolarizing wave will move towards the basal part. So the basal part of the heart is the last portion to be depolarized. So the third electrical activity is the basal depolarization. So we can say that the first electrical activity in a cardiac cycle is atrial depolarization. Its vector is downward and to the left. It is small and of moderate velocity. AV nodal stimulation, when it is happening, the electrical vector is small and slow. And ventricular, when we are considering the ventricular depolarization, we have to divide it into three types or three sets. One is a septal depolarization, will give a separate kind of vector, and the major ventricular depolarization, which will give rise to another kind of vector, and the basal depolarization will generate some other type of electrical vector. So now we want to see what are the different types of vectors they are going to produce.